Hello everyone, greetings from India. This is Nirbhay Chauhan from Eklavya Self-Learning Tutorials. Well, today I'll be giving a detailed presentation on my thesis research work, the project which I have discussed in my last video, in which I explained about this IFC rule engine for the structural code compliance. Well, today I'll be giving a detailed presentation about that project. Well, this was my thesis project for my MTech in structural engineering, and my supervisor is Dr. H.S. Rai. So the thesis part is completed and the research has been done. My MTech has been completed, but that's the part was for the academic part. But now the project has to be taken to a new level, I should say. So today I'll be giving or presenting this detailed presentation about the research that I have done, about the objectives, the references that I took, the previous literature work, all those such stuff. Well, let's start with that. The title for the thesis is Computer Aided Code Compliance of RC Slab, that is Reinforced Concrete Slab. And this logo is of my college, this logo, that is Guru Nanak Dev Engineering College, Ludhiana. So let's start it. So before proceeding directly towards the research and all those things, firstly we need to see the introduction to the problem. What is the problem prevailing in our society in the AEC industry? Like the very first is building must be verified with local design codes before the construction. This is done so as to ensure the public safety. And as per present practice, if we see, the structural code compliance is done manually. Such manual code compliance is a very tedious task. It becomes so complex and it often causes ambiguity and also delays the project. And this also results in several unwanted errors in the designing phase or in the construction execution. And for this problem, we have used BIM, that is Building Information Modeling, and its open source, or I should say the open format, that is IFC, Industry Foundation Classes, as a base to this problem. So next, let's have a brief literature review about the previous works that has been conducted. So let's start with the very first work of Singapore. So in this paper of Patrice Poirier in 1997 dated back, the implementation of CoreNet, that is a construction real estate network where the plan checking system was done. So this is a technical report. So this was the first initiative in automated code checking system, and this was entirely based on the ISO 10303. 10303. So this is basically the step form a code. So regarding the all those retail project, I should say. Next, this was aimed to provide an internet-based electronic submission system for checking and approving building plans back then. So that was a quite interesting thing. And then in 2002, this was carried forward by commissioning Phonex. So this was addressed by ePlancheck. Then if you see, Phonex is an independent software network and where each object is designed to be extensible in order to cover the requirements of other countries also. So this was a huge breakthrough for the automated code checking system. I should say the first initiative, and this was a remarkable thing. Next, moving towards Norway, the paper by Haraldsen in 2004, where developing e-government portals was a project. So from life-saving events to generous to requirements in the 11th Norwegian Conference on Information Systems. Here the corner work was carried forward and developed an emulator in Norway with the Big SOC system then, and this was heavily based on IFC standards, which is a good thing to see. And currently they're focusing on the issues of classifications, terminology and standardizing rule checking in construction system as per this paper. Right now they have made a huge contribution to the whole of the global automatic code checking system, and right now they are by the company AEC3 in UK. It's a consulting firm and they're doing pretty good jobs there, and they're really contributing to the standards also, and they're also, as a I should say, building smart chapters. They are making huge developments and contribution to the open BIM also. Next, by Ding and others in 2004, it was for Australia where automatic code checking system for the clients driving innovation, moving ideas into practice. Here it was something proprietary based where both the SMC, that is the solid body model checker, and the EDM, that is Express Data Manager, which is the software library, were considered as possible platforms for automated code checking. And this project was undertaken by CSIRO and University of Sydney. Here the design check uses object-based rules encoded using EDM, and the building data models in IFC format are imported into the EDM database and transformed into the design check internal model. And as per now, there is no further development in this project. Next, if we see in USA, this is a very interesting project in 2006, where GSA BIM Guide, that is a Global Spatial Administration, sorry, General Service Administration BIM Guide for Spatial Program Validation Appendices. So this was carried by, I should say, two key persons, the Bill East and the director of AEC3, Nicholas Nisbet. And here the initial emphasis on health, safety, and welfare was given, and they developed smart codes. This was a project driven by the ICC, International Code Council, and this was focused largely on the addressing the problem of transforming paper-based codes into machine interpretable rules, that is the digital codes. This is something we also done in our project. And the rules are then automatically extracted following a strict mathematical pattern into an IFC constraint schema. So this was something also a breakthrough project, and right now they have done a lot of advancements in their project. You see, go through their websites and the GSA, a lot of things has been going for the plan checking as well as the other government portal projects. So that's one thing I suggest all to just refer once, not once I should say, again and again, to just learn and see what these guys are doing. It's a pretty good job. Next in India, the paper by Dhillon, Arking and others in 2014. Here the paper was parsing building data from industry foundation classes through IFC model parser. This was a project where IFC model parser was developed, and this was a GUI based application, parses IFC models and exports them to Excel spreadsheets and text file. And results can also be displayed on the console application if required, and the project is capable of determining the minute details of the model and create the Excel sheets on the fly. This was quite quick and efficient, I should say. And the test has shown that the project can handle creation of hundreds of worksheets per model without any problem. So next I should suggest some essential reading for you guys, which are very helpful. I should say the base for all these developments, which have been very essential to the previous projects, and these are also helpful if you're developing anything regarding IFC or open source things. So you must refer these things. So these are basically the paper by Nisbet and Elif Hajelset, and these are some of the essential papers I should suggest everyone to read. So next, here is a brief comparison that I was done for the various code checking system. If you see, a table has been drawn here where the projects of the various countries, Singapore, Norway, US, Portugal, Canada. The brief comparison has been done, and the references also been quoted from which they have been. I have just taken the references. So entirely has been things done like which have been based on the IFC and what the rules were coded in and the checking system names. So this is a brief comparison, I should say. Next, after having this literature review, we should move forward to the research gaps that we pointed out. Like there is limited general publications on automated code compliance of building structural components. So this is a very important thing that was the key for us, that we moved towards the structural system, as my domain was also structural engineering, and there is lack of open-ended research in this domain. That's also something to be noted down. No doubt there are pretty impressive researches which has been done, but our main motive was for the structural code compliance. And there is no rule engine for code checking of the structural design of buildings using IFC. This was our main focus, that is the industry foundation classes, which point towards the level 3 BIM. At now, if you see, level 2 is in the run to be implemented, and many countries are leading towards. The UK at number par at par first, so they are going to level 2, but our focus was for the level 3, which is the ultimate goal for the BIM. And next, there is limited or no use of open source technology. No doubt there have been works done. The many leading works have been done for the e-plan checking system, e-plan checking system, and other projects. But again, we see there is limited open source technology. And then there is least consideration for the open standards. The open standards are being developed, but the leading BIM software are not able to, I should say, they are able, but are not implementing much. And lack of interoperability among different workstations also is a problem, and there is limited contribution to a common platform. And next, if we should see the research objectives that we formulated, the very first is to study the entity's definition, their pattern, types, their relations, and their particular hierarchy of the IFC files, which are in the IFC 2x3 documentation. And we need to prepare the required code checks for RC slab as per our Indian standards IS 456 2000 revision. And we also need to extract and arrange the desired information from IFC file to a custom rule engine where we could apply our digital code checks, and to develop such a framework to apply prepared code checks for the purpose of our code compliance. Next, the scope of work can be briefed as we are to ease the present complex structure code compliance system, to decrease the manual redoing of work, to step in a direction to improve interoperability, which is a major issue. The interoperability issue is a major issue going on in the whole BIM industry. Like there are plenty of number of softwares in the BIM field, but the interoperability is the main issue that is in lagging behind the whole industry. Then to encourage the use of IFC and the common platform to exchange information, that is the main priority, and to promote the use of open source technology and open standards. And also we are contributing this research to the open BIM movement. Next, here's a brief methodology I should say that I've used for the research. I'll be explaining here. Like the very first was to study the previous code checking system, like in which in the field of our code compliance were referred, and the structure of the rule engine was also analyzed. Various loopholes and drawbacks were identified. The basic approach to program those code checking engines was also considered for further analysis. Next, exploiting the IFC, this is very important, I should say. Like before building a custom rule engine, we need to thoroughly study the IFC entities. Their definitions and their respective hierarchy trees need to be carried out. And detailed study was also carried out to match the properties of various structure elements with the corresponding defined IFC entities. I'll be showing in later one slide. And next, different BIM software use different software libraries. Like to produce IFC file, or does Revit use Express Data Manager EDM as I just told earlier, and FreeCAD use IFC OpenShell. Next, here is a typical example of a header file produced by one of the software Revit. So here you can see the ISO 10303, that's a base step code. Then you can see written step physical file produced by the EDM. Then here's the creation date, schema creation date, model creation date, header model, license ID, and all such details. Next, we need to refer the ISO 2x3 documentation. If you see, there are a total number of 653 entities which are defined in this revision. So they were pretty good. We didn't move towards IFC 4 because IFC 2x3 also has the same amount of definition that we required in IFC 4. So this was quite satisfactory. There were some loopholes, but before that we made us propose, or we just need to tell the general construction hierarchy. If you see, there is a site at first. If you see in the construction industry also in the site, we had to first locate a site. Then there can be several buildings there. We need to make plans. Then in every building there can be several floors or levels, or if you say building stories. Then each building story then can be different components. They can be structure components, they can be architecture components, or the MEP fittings. So our focus was on structure components. Then we can see slab beam columns, and each of the structure components have their respective reinforcement details, that is the rebars. They are embedded in these parent structures. Next, IFC also describes a building hierarchy, like the building IFC building we have, then we have the IFC rel aggregates, how the buildings are grouped, and IFC space, IFC rel containing structure, IFC rel containing spatial structure, how the building elements, walls, slabs are grouped. Next, if we see the building decomposition is also very well described by the IFC, like how the IFC building further decomposes into different like IFC stair, IFC wall, how these things can be grouped through the use of entities name, IFC rel aggregates. These group the IFC building stories. Then we have the IFC rel containing spatial structure. Those are grouped for grouping the wall, stairs, members for the particular level or the building story. Next, a typical inheritance graph. As per IFC, the inheritance graph, you can say it's like entities and further entities described. So we made a simple inheritance graph by understanding, like if you see example of IFC reinforcing bar. So we have the description properties, the naming, description, owner history, global ID, and further we have the properties like object type, object placement, representation, the tag, the steel grade, dimension properties may include nominal diameter, cross-section area, bar length, bar roll, and the bar surface. So this is a typical inheritance graph of a particular entity. IFC slab may have some other type of inheritance graph, then IFC wall, IFC beam, and so on. Next, if we see, we need to exploit the parsing functionality of IFC OpenShell as we use as a base for our Python program. And the two key functions which are present in the IFC OpenShell that we use. The very first is by type argument. Here, the user is able to extract the desired type of information. The information may be like IFC project, IFC site, IFC building, etc. For example, if a user wants to fetch the data of IFC slab, then it can be done by simply writing IFC slab as argument, that is by type IFC slab, and we'll get all the details of a particular entity. The next is a. Here the user uses this function in two different manners. For example, it can be used without filling any argument, then it will deliver the user about the relation of the information present with any entity. Secondly, if a user uses this function by filling any argument, that is a ISS slab, then a verification of the name of the argument with the name of the entity is done, whether they are same or not, and the result is delivered in the form of true or false. So these are basic two things we use in program. Next, we move towards preparing the structure slab model which we need for the purpose of our code checking. At the very first, we prepared some sample structure slab without any boundary condition or any spatial condition, just simple structure slabs and with simple reinforcement details. Then we move towards the creating of the slab with particular other structure member also, like beams, columns, and footings. Then we moved towards building several slabs in particular direction or particular level, then in different direction. Then we made slabs in different levels and we made our code in accordance to that, and we further progressed by increasing the levels, then by different types of slab, cantilever slab, fixed slab, continuous slab. Then we made our more realistic models by implementing the typical architecture details like terrain, walls, openings, like such. And then we prepared the code checks. We referred this IS 456, the plane and reinforcement concrete code of practice. So we prepared our code checks. We prepared digital code checks in accordance to this code, which are required for the purpose of slab. And these are all the code checks that we prepared. Their particular closed, their formula, their notations, like maximum reinforcement required, minimum diameter, control of deflection, spacing, moment capacity, load carried by slab. So these are around 19 or 20. And then I'll be showing how we process the IFC data. Like the checks were coded into digital formulas considering the relation of the notation with the IFC entities. Like for better understanding, let's consider an example below. Like how the dimension of the slabs were fetched. Like we know we gave the input like slab depth, then we just formulated like first we need to go to the slab representation, then we have the representations, then the first entity 0 represent the first entity, then we have the items. In first entity of the items we have the depth, like so we made the slab length like the sept area x dimension, and the slab width that was the sept area y dimension. So this is how we understand the IFC entity spectrum, the definition, and we move towards by formulating our formulas into the digital checks, and we store the values in our Python code. Then the results, like the graphical procedure is explained below, and we propose the usage of this whole scenario with the use of bimserver.org, that is an open source BIM server. Like you can install on your dedicated server or your local host. Like you can see, the different professions can work on the project, like an architect, structure engineer, contractor, and there can be several revisions also which are given here. Uh, any several number of projects can be added. Like you can see here, a slab is added or a particular building, and we can perform several impressive operations here. We can also query the information. We can further, the main thing we can download our file in for several formats like IFC 2 by 3, IFC 2 by 4, in JSON format. So next, after downloading, we made our files stored where our Python rule engine.py is stored. And next, after running in the PowerShell, it asks to enter the file name, and we enter the file name. I have explained this whole procedure in my last video where I have given the working demo of my rule engine. So after, you can also refer that video for a proper good visualization. So after entering the name, we have to enter the name without any extension like .ifc, simply entering the name, sample building. Then it will open the file, it will process the file, and it will show us all the levels contained in that building. So we'll be enter any level name which we desire. Next, after entering the level name, it will show us all the slabs contained in that particular level with their names. Then we can enter any of the slab name, and after entering, we get a detailed report for our code checks, like what is the nature of the slab, it is two-way or one-way, the checks are failed or passed, if they are failed, by how much value are they failed. Like there can be several advancements also in this report, like we can also mention the clauses name, which clause is getting failed, or we can also generate the multiple reports of all our slabs at once. So the project can be taken forward to an extent if you see. So it was quite satisfactory for the purpose of thesis, I should say. But we are planning to make it more and more practical in nature. So we're moving aggressively forward. Next, if you see, there are some important discussion like instances where the present BIM software often fail to follow the IFC implementation standards. Like there is absence of the relation between rebars and their parent or hosting structure members, like we face in the problem Revit and Tekla. But the users claim, like in ArchiCAD, we can make the grouping through IFC rel assigns to group, which is quite impressive thing. I'll be looking forward to that. And then the bar role for the independent IFC reinforcing bar was missing. However, they were grouped by, for the steel grade, they were not defined, but they were grouped by the IFC material, where different IFC reinforcing bar, their material was defined. But I feel it should be also present in individual reinforcing bar also. And there is no implementation of the IFC rel reference in spatial structure. Well, this entity is used, suppose you have a reinforcing bar which is starting in a beam and then going to a slab, and then again it is ending in other beam. So we know that that particular reinforcing bar is contained in that slab, but this is also referred by two beams also. So this was a very important entity which was not defined. So if we face such difficulties, next, the conclusion that can be made, like the main deliverable of this research is tapping in the direction of automation design, and the tedious and time-consuming process of manual code checking can be completely eliminated with the code checking engine developed in this research. However, it is in initial phases. The framework developed can be easily extended further for the design checks of other RC structure elements also, like beam, column, and footing. We need to just make their digital code checks, and their IFC entity need to be grouped and related with the dimension annotations we need, and the code checks can be done. So it is open-ended research. So the future scope that we can formulate in brief here, like the developed framework of the rule engine has a provision for additions and modification as per the need of code checking of other RC elements too, as I described before. The another similar framework can also be developed for the design check of various design software using their output report. For example, StatPro export a text file which can also use for processing, and we can make a database and further the operations can be done. Then the information from the output file can be arranged in a custom database from where the user can perform the desired operation required for the purpose of code compliance. Further, the developing of such open format code checking engines can highly encourage the use of OpenBIM and open the gateway to level 3 BIM, which is the main target for whole researchers all around the globe, and they're working aggressively and quite well to make the level 3 BIM in more reality. And I believe this can be done by the open standards and the open formats only. And the base that earlier I have told and we have used, that is IFC, Industry Foundation classes. Next, these are some of the references that I can just conclude here. You can just also see, which was these references were quite important, I should say. And the one I have told earlier, which are the essential reading, you should also refer those also. And next, if you have any question, please feel free to ask in the comment section below. And if you have any suggestions also, please feel free to tell. I'm ready to accept the suggestions and all those things, because we are eagerly working to develop more and more for the OpenBIM things. Well, thank you so much for watching this. And there are some persons, some key persons that I want to acknowledge for this. Like the very first is my guide, Dr. H.S. Rai, because of whom this research, uh, I should say, we have taken to so much a new level. I never thought 2 years back that I will be making such thing, but progressively the things happen. And my programmer friend, that is Amit Pal Singh, he also worked for the GSOC project for developing the rebars of the FreeCAD. He has also contributed a lot for the coding part. And the developer of FreeCAD, Yorick Van Havre, thank you so much. He is also cooperating, readily available for any of the questions. And all the, I should say, BIM community from all around the world, the BIM researchers who have been helping me directly or indirectly, the research papers of whom I have read. So they all have been pretty much helpful to me, and all the researchers and all the consultants, I should say, and some special thanks to the Nicholas Nisbet, the director of AEC3, who personally has given me some suggestions some days before for my IFC rule engine. Thank you so much, sir. And all the previous projects which has been done for the Open BIM, I'm really thankful for them also. Like they have been an inspiration for the persons like us and the research and to move forward and just develop more things in this domain. So that's all for today. Well, thank you so much, guys. This was Nirbhay Chauhan from Eklavya self-learning tutorials. We'll see you in any of the next video tutorial. Goodbye. Thank you so much once again.